Wave equations and graphs. If a wave moves up and down in simple harmonic motion, then the wave is mathematically represented by a sinusoidal function, sine cosine. In this case, a mechanical oscillator is moving the string up and down with a constant speed. So again, here's your trough, the lowest point, here's your crest, the highest point, and the amplitude is between the crest or the trough and the center line here, the equilibrium line. The motion of a wave can be described in two ways, and the graphs and wave equations will be shown for both. The first graph that we'll show shows how the displacement, or x of the wave from equilibrium, varies as a function of time. So that's what? That's a displacement time graph. The second graph shows how the displacement, y of the wave from equilibrium, varies as a function of its position. So that's a position-position or displacement-displacement graph. The amplitude of the wave is the same for both graphs. The period, t, is the distance between two crests or troughs on the displacement x versus time graph. For transverse waves, the displacement is in the vertical direction, for a wave moving like that. For longitudinal waves, the displacement is in the horizontal direction, the same as the direction of the wave. But the displacement for longitudinal waves is drawn on the graphs in the vertical direction to separate it from the wave's motion. And you'll see hopefully in the next few graphs why that makes a little bit more sense than drawing it in the same direction. The displacement as a function of time is found by using the below wave equations. The first two equations are shown on the AP Physics 2 Table of Information equations. The period, t, is the distance between two troughs or two crests, which are shown here, or any part of the wave that repeats. So for example, between here and it goes up and down, then it starts repeating here, that would also be the period. Here are the wave equations, where omega is equal to 2 pi f. And down here, what did we do? We replace frequency with 1 over the period. Now for displacement versus position of the wave's wavelength lambda, this time that's what we're measuring between the crests. That's the distance between two crests or troughs on the y displacement versus the x position graph. For a transverse wave, y as a function of x is perpendicular to the wave direction. For a longitudinal wave, y of x is parallel to the wave direction. And here's our wave equation for the displacement versus position of the wave. The height of the wave as a function of time is presented by the graph below. What is the period of the wave? What is the amplitude of the wave? Then construct an algebraic equation that describes the graph. So here's our position and here's our time. The period of the wave is the time between two closest points on the graph oscillating with the same phase. It's a tricky way to just say I can go from here, for example, to here. Right? They're at the same point, and it's going in the down direction there, and it's going down direction there. Or an easier way is just take the distance between two crests or troughs, and in this case we get 2 seconds. The amplitude of the wave is the maximum displacement of the wave from the equilibrium position. This time, from the graph, you go from here's your equilibrium position, the max over here is 4, and over here is -4, and we just need the amplitude, which is 4. Please remember earlier we said you could use either sine or cosine, and in this case, since x of t equals 0 is equal to 0, we're going to use the sine function. So here's our wave equation. We found that the amplitude was 4. And what did we find for the period? The period was 2. So 2 divided by 2 is 1. So this is our wave equation for this motion. This time we have a displacement position graph. And we want to find the wavelength of the wave, its amplitude, and an algebraic equation that describes the graph. The wavelength of the wave is the distance between two closest points on the graph oscillating with the same phase, or we can just take the distance between two crests or two troughs. So let's see what we have here. Over here, we have one crest. Over here, we have the next one. The distance between them is 1 meter. So the wavelength is 1 meter. The amplitude is the maximum displacement of the wave from the equilibrium position. In this case, here's your equilibrium. Our distance away is 6. So the amplitude is +6 or -6. This time, we're going to use the cosine function because y as a function of time, where time is 0, is equal to a. So we're going to use this wave equation. We substitute in our amplitude, which is 6, and then our wavelength, which is 1, so we just get 2 pi over 1, which is 2 pi. So y as a function of x is 6 cosine of 2 pi x.